Hello, this is Dr. Gardner. We're continuing from where we were last time discussing intermolecular forces. Last time we have been discussing about induced dipoles as well as London dispersion forces, and then we were comparing those to dipole-dipole interactions when we had polar molecules. Now, some types of polar molecules have a permanent dipole present in them that is very strong and tends to be somewhat unique compared to the strength of dipole-dipole interactions between other similar polar substances. And so let's discuss where we might give a unique name to these types of very strong dipole-dipole interactions. So if we consider some trends on the periodic table, if we look at oxygen, sulfur, selenium, tellurium, if we look at this as we have increasing molar mass from dihydrogen sulfide, dihydrogen selenide, dihydrogen telluride, as we're going from left to right here, we see an increasing in the boiling points, which we could relate to those increasing molar masses. But we notice that H2O, when we look at the first element in that group, in that column on the periodic table, we have a much higher boiling point. And we notice that's the same for fluorine bonded to hydrogen, nitrogen bonded to hydrogen. Okay, we see those cases we have very high boiling points, but when we get to carbon bonded to hydrogen, we see the trend as we go from methane to silicon tetrahydride, to germanium tetrahydride, to a tin 4 hydride. We end up seeing as we go from left to right that we have an increasing boiling point as we're going down the group. So why do we have a unique situation when we're looking at water, hydrogen fluoride, and ammonia? Why do we have high boiling points there? Well, one thing we can think about is we have a very large difference in electronegativity. So we're looking at hydrogen, which is very electropositive, and we're looking at some very electronegative elements such as oxygen, fluorine, and nitrogen. So really I can say, well, hydrogen is directly covalent bonded to one of these three atoms: fluorine, oxygen, or nitrogen. We get very polar bonds, and we tend to get very strong dipole-dipole interactions between those molecules on the next adjacent molecule that has such a strong dipole-dipole interaction. And so we give these a unique name. We call this hydrogen bonding in this case. This is occurring because we have the very electropositive hydrogen, the very electronegative fluorine, oxygen, or nitrogen. And not only is it the difference in electronegativity, the sizes of these atoms are quite small. You'll notice the fluorine, oxygen, and nitrogen are all in the second period on the periodic table. So we're in the second period here. They're very electronegative atoms. Because we're in the second period, they're also much smaller than the elements further down the periodic table. Now, the reason carbon isn't on this list is you'll recall as we go from left to right on the periodic table, the size of our atoms is actually decreasing. So carbon's a little bit bigger in size and a little less electronegative than nitrogen, fluorine, and oxygen. So it's these very small atoms that are very electronegative when they're bonded to hydrogen that we have a very strong dipole. And so we have that unique situation with higher boiling points for those atoms as they're bonded to hydrogen, and we say they have hydrogen bonding capabilities. Now we have to be very careful. I can't just assume that any molecule that has hydrogen in it and one of these electronegative atoms is capable of hydrogen bonding. They must be directly covalently bonded to one another. If we have them not directly covalently bonded to one another, then the difference in electronegativity between hydrogen and another element it might be bonded to is going to be much smaller difference. We may have sizes of those atoms which may not both be very small, and so we don't have such strong dipoles in those cases. So it's very important you look for hydrogen directly bonded to one of these three atoms. So when we're looking for hydrogen bonding, as I said before, we look for nitrogen directly bonded to hydrogen, oxygen directly bonded to hydrogen, or fluorine directly bonded to hydrogen. Okay, those are the three cases that I'm looking for. We would expect that the dipoles, the permanent dipoles in those types of polar molecules would be very large, very strong, and that we'd have strong intermolecular interactions between these types of molecules and similar very polar molecules that are capable of hydrogen bonding. And so in those cases we expect to have high boiling points, high melting points. We tend to expect to have low vapor pressures. We would expect to have high surface tension. So we would expect those intermolecular forces to be strong and to influence those types of physical properties. Okay, so that's where we were seeing the high boiling points on our previous graph. It was because of the very strong intermolecular interactions. And it's kind of interesting because these types of very strong types of hydrogen bonding can produce unique shapes between these molecules, and that's important. For example, as water freezes, we notice that it's kind of unique that the density for ice is less than that for liquid water. One of the reasons for that is the hydrogen bonding that can occur here. These strong dipole-dipole interactions causes a hexagonal crystal structure in the ice, which has some spaces left in it. So it's that strong intermolecular interaction and the organization it causes with respect to the types of shapes in the systems we're looking at that results in the lower density of ice. Now, in living systems, when we start to look at hydrogen bonding in biological molecules, this also will cause certain shapes to occur with biological molecules that are very important, as I'll talk about here in just a second. So we really want to think about how hydrogen bonding and its strong intermolecular interaction will produce specific shapes in nature. Now, if we're going to try to classify hydrogen bonding, let's draw dotted lines between the molecules as they're forming hydrogen bonds. So let's say we have a bulk water sample. If I have a bulk water sample, here I have my hydrogens bonded to the red oxygen, and so this follows my H-Fon rule, right? Hydrogen bonded directly to either a fluorine, oxygen, or nitrogen. In this case, it's an oxygen. We end up with a very polar molecule here with its dipole, and so I'm going to show with the positive end of the molecule a plus sign and an arrow here towards the negative end. So we show a Greek letter delta negative for the negative end of the dipole. Out by the hydrogens, we're getting positive ends of the molecule, so we end up with less electron density on that end. And this very strong dipole is what we're calling a dipole-dipole interaction with a special name that we say can produce hydrogen bonds. So I'm showing dotted lines where the hydrogen bonds are occurring. So you'll notice the negative oxygen will be attracted to the positive hydrogen in the next molecule over that has such a strong dipole that's capable of hydrogen bonding. So water molecules bonded to other water molecules are bonding through the intermolecular interaction, which we're defining as hydrogen bonding. Remember, it's just a really strong dipole-dipole interaction that's somewhat unique by its strength. Now, if we look at ammonia dissolved in water, and well, ammonia is fairly soluble in water because we can have hydrogen bonding between the water molecules and the ammonia molecules. Again, we're getting these very strong dipoles that we're calling hydrogen bonds that are occurring between these molecules. So here I have the hydrogen white atoms with their delta positive being attracted to the nitrogens here in the ammonia and their delta negative. And so the very strong dipoles we have here is hydrogen bonding, and that's what I'm showing for a dotted line. So I get hydrogen bonding capabilities between water and ammonia because in both cases we're following the H-Fon rule. So here we have hydrogen and water directly bonded to oxygen, which is what we were required in the molecule. And here we have nitrogen directly bonded to hydrogens, 3 hydrogens in this case, 1, 2, 3. And since both of these have those very strong dipoles that meet the hydrogen bonding criteria, we can expect that these could hydrogen bond together. Now in bulk ammonia, well, the ammonia molecule is going to have hydrogen bonding because again I have the very positive hydrogens that are bonded to the very negative, electronegative small nitrogen atoms, and so I get the intermolecular interaction of hydrogen bonding that's being donated from this ammonia, and it's being accepted here by the center ammonia. So I'm getting this hydrogen bonding here as well. If I look at hydrogen fluoride, again, that follows the H-Fon rule. So here I have hydrogen directly bonded to the small, very electronegative fluorine. Right? So here I have hydrogen that's very positive, and here I have fluorine that's very negative, and so the interaction between molecules is producing a hydrogen bond that we've showed in as a dotted line. So that's a common way that we will show hydrogen bonding is dotted lines between the molecules to represent these intermolecular interactions that are occurring. Now, as I said, biological molecules take advantage of this, and one of the most important examples we could probably talk about would be a DNA. When we consider DNA, well, the double helix of DNA is occurring because we have each of the strands of DNA producing hydrogen bonding between the base pairs. So here we have cytosine and guanine as our base pairs. We can see here I have nitrogen, and here I have hydrogen, so that follows my rules for hydrogen bonding. So here I have a donor of a hydrogen bond from this very polar dipole between nitrogen and hydrogen. Here I just have oxygen. So oxygen isn't directly bonded to hydrogen, but it can still accept the hydrogen bond from this amine group from the cytosine base pair. And here I have nitrogen not directly bonded to a hydrogen, but over here I have nitrogen directly bonded to a hydrogen. And so what I have in these cases is when I see hydrogen directly bonded to Nitrogens, these are good sites where we get very polar dipoles, and so they're good hydrogen bonding donors. But we can have a very electronegative small atom like nitrogen or oxygen or fluorine on my molecules could accept the hydrogen bond, but they wouldn't be able to donate that hydrogen bond unless they had directly been bonded to a hydrogen. So it's kind of a unique scenario here. You'll notice that the base pairs will form hydrogen bonding between them so that you have complementary base pairs in biology. So the cytosine and the guanine have two hydrogen bonds between them, so there's a nice fit between the shapes and where the hydrogen bonding can occur so that we have those complementary base pairs, whereas adenine and thymine, they have three hydrogen bonds present between them, so they're a good complementary base pair because of their shape and where the hydrogen bonding can occur at. So this is why we get those complementary base pairs. Without this type of hydrogen bonding occurring, DNA wouldn't function the way that we know that it does now. For example, when we replicate DNA in our bodies, what's going on is we basically have the hydrogen bonds between the base pairs and this double helix kind of unzip. We break those hydrogen bonds, and then we're able to bring more base pairs in and synthesize a new DNA strand as we start to replicate the DNA, and we're producing the new strand because the base pairs will organize themselves where these complementary hydrogen bondings are occurring. Okay, so it's very important with respect to understanding biology that you understand intermolecular forces. It's just something kind of interesting there. Now let's consider some of the unique character of this. I mentioned before that when water is forming hydrogen bonding as it freezes to form ice, well, in the liquid state we have more freedom of motion between the molecules, more disorganization, but when we form a nice crystalline lattice as H2O freezes to form ice, we notice that the hydrogen bonding between the hydrogens here and each of the oxygens, as we form those hydrogen bonds, we form this kind of hexagonal shape, and so we get these hexagonal channels in there. So we have all this empty space, right, that's here in the ice crystals, and so we tend to have a lower density. And liquid water versus ice, the ice will expand. So if you forget and leave water in your freezer, let's say in a glass bottle, there's a larger volume for the ice than there would be of the liquid. And so we notice in this picture here we've basically cracked and shattered the glass bottle that's been frozen because of the expansion of the ice as we are forming nice organized hydrogen bonds in the ice crystalline lattice. Okay, so that's what we're seeing here. That's why ice is less dense, is because of the hydrogen bonding organization of the molecules. Now let's look at a few different molecules that may or may not be capable of hydrogen bonding, and let's see if we can classify which ones can hydrogen bond and which ones would not be good donors for hydrogen bonds. Okay, so here we have a molecule that's CH3NH2, so this is called methylamine. This methylamine molecule, let's decide if it's capable of hydrogen bonding. Now I have to be careful. I can't assume just because I see hydrogen in the structure and just because I see fluorine, nitrogen, or oxygen in the structure that it's capable of hydrogen bonding. They need to be directly bonded to one another, so it's often helpful if you draw the Lewis structure. So if I look at the methylamine here, what I can do is draw out its Lewis structure, and I have these three hydrogens directly bonded to the atom before them, to the carbon. So I have these three hydrogens bonded. To nitrogen, which has two hydrogen bonds off of the nitrogen and a lone pair. So if I look at the Lewis structure here, we need to ask ourselves, are we following the H-Von rule? If I look at the H-Von rule here, I can see that hydrogen is directly bonded to nitrogen, a very small electronegative atom. So we're definitely following the H-Von rule here. In this case, we're going to go ahead and have hydrogen bonding capability. So I'd say yes, this molecule is capable of hydrogen bonding. Now let's consider another molecule. Let's consider nitrogen trifluoride. If I consider nitrogen trifluoride, in this case there's no hydrogens in the molecule. If I look at the molecule's Lewis structure, we have our three fluorines bonded to the central nitrogen. When we draw the Lewis structure, and we have a lone pair off the nitrogen, but there's no hydrogen present in the structure at all, so it doesn't follow the H-bond rule. So even though I would have a permanent dipole, and I would have dipole-dipole interactions between nitrogen trifluoride and the next nitrogen trifluoride over, it isn't capable of hydrogen bonding at all. So in this case, we would say no hydrogen bonding, so we don't expect it to have a uniquely high boiling point or uniquely strong intermolecular interactions. Now let's go ahead and consider dimethyl ether. Okay, if we consider this molecule, there's hydrogens in the molecule and there's oxygen, but I really need to draw the Lewis structure to see whether or not the hydrogens are directly bonded to the oxygen. So here we have carbon bonded to the oxygen, and then we have a second carbon bonded, and I have 2 lone pairs on the oxygen. But these 3 hydrogens are bonded to the carbon before them, and that's usually what we'll expect from seeing a structure like this. The hydrogens are bonded to the atom before them in the structure as written out. And then the last carbon in the structure has its 3 hydrogens listed after it bonded to it. And so when I draw this Lewis structure out, we can see that even though there's hydrogen and oxygen present in the structure, the hydrogens aren't directly bonded to oxygen. So we don't get those very strong bond dipoles from the very large difference in electronegativity. In fact, if we look at hydrogen bonded to carbon, the electronegativity difference here is not that different. They're somewhat similar compared to hydrogen versus oxygen. So this isn't a very strong bond dipole. So this molecule isn't capable of forming really strong molecular dipoles, unfortunately, in this case. So it doesn't form strong hydrogen bonds. So I say no, it is not capable of hydrogen bonding in this case. It does not follow the H-bond rule. Hydrogen is not directly bonded to oxygen. Now, if I look at ethanol here, well, we have carbon with its 3 hydrogens bonded to it in this structure. And I can see these 2 hydrogens are bonded to the second carbon in the structure in ethanol when I draw the Lewis structure. And I can see this last hydrogen is actually bonded to oxygen. Now that was the important one, because if I have oxygen that's directly bonded to a hydrogen, this is an alcohol group. But if I have that type of OH type of group in a molecule, hydrogen is directly bonded to oxygen, so that follows the H-bond rule, right? Hydrogen directly bonded to one of my very small electronegative atoms, such as fluorine, oxygen, or nitrogen. So in this case, we end up having hydrogen bonding capabilities in ethanol. So ethanol is completely miscible in water. It will dissolve in any ratio because it's forming these type of intermolecular interactions that are similar to that of what water molecules form between one another, because it's capable of hydrogen bonding as well. So it can donate hydrogen bonds from this group, as well as accepting hydrogen bonds, because it has a very electronegative oxygen and the very electropositive hydrogen here. So if I have a water molecule nearby, we can expect that water molecule nearby that has the very polar bonds in it and a very strong molecular dipole to be able to accept a hydrogen bond here with dotted lines between this hydrogen and that oxygen. And then we could also have another water molecule over here in the bulk liquid that has another hydrogen oxygen type of bonding situation. So it's a very polar molecule as well, and we can end up with hydrogen bonding where the hydrogen is donating its very positive electronegative character here with a very negative electronegative character of this oxygen. So I get these hydrogen bond in this location and a hydrogen bond here in this location, and then I get a variety of those occurring. So it's these OH groups that we expect to produce those. So methanol, propanol, other types of alcohols can hydrogen bond, and they're quite soluble in water, unless this carbon group becomes quite large. If the carbon group is quite large, then we might expect that it will not be very soluble in those situations. Okay, now let's consider HCl. Now if I have hydrogen chloride, or if this is in water, it would be hydrochloric acid. If I consider it, even though this is a polar molecule that can form dipole-dipole interactions, we can expect that this would not form hydrogen bonding because I have hydrogen bonded to chlorine in the Lewis structure. I do not have it directly bonded to fluorine, oxygen, or nitrogen, so this does not follow the H-bond rule. Remember, my H-bond rule was hydrogen had to be directly bonded to one of these very small electronegative atoms, nitrogen, oxygen, or fluorine. Okay, here we have chlorine. Even though we have a strong dipole, it's not as strong as these hydrogen bonding types of dipoles. Okay, so I would say no here. Okay, so if I were to look at the following substances and try to decide which one of these in their pure liquid state would form hydrogen bonding, I need to follow the H-von rule, maybe draw the Lewis structure out, and decide if they're capable of hydrogen bonding. So here I have hydrogen and nitrogen all in the same molecule. If I draw the Lewis structure out, we can see that we have trimethylamine, so we have nitrogen directly bonded to these three CH3 groups. So I'm seeing three of these groups all bonded to that nitrogen. The best Lewis structure we can come up with will have all three carbons bonded to the nitrogen. Now this immediately tells me that I do not have a hydrogen bonding capabilities because hydrogen is not directly bonded. Well, notice these three hydrogens are listed after the carbon. That's a hint that they're bonded to the carbons in this structure. So I have three hydrogens bonded here and here. And then here I have three hydrogens bonded. And so it's a somewhat larger molecule than the ones we've been looking at previously, so the Lewis structure is a little more complicated. But again, hydrogen is not directly bonded to the nitrogen, so we'd say no in this case. So no hydrogen bonding in that case. Now let's consider acetic acid. This is one of the formulas for acetic acid. If we look at acetic acid's Lewis structure, well, these three hydrogens are bonded to that carbon. These two oxygens are bonded to that carbon. And this hydrogen is going to be bonded to one of those oxygens. So now I'm seeing hydrogen bonded to an oxygen, so I'm expecting hydrogen bonding capabilities. Let's draw it out to confirm that. So I have that first carbon with its three hydrogens. And I have our second carbon, and it's going to have a double bonded oxygen in one position with its lone pairs. Now this oxygen isn't involved in producing a hydrogen bond. It might be a hydrogen bond acceptor, but it doesn't have hydrogen directly bonded to that oxygen, so that one doesn't meet the bill. But the second oxygen in the structure would have its two lone pairs, but it would also have hydrogen forming a covalent bond to the very electronegative oxygen. So here, this meets the H-von rule. So this definitely could produce hydrogen bonds and donate hydrogen bonds from this location. Okay, so this one would be a yes. So we expect higher boiling points, higher melting points of this substance. We expect it to have greater surface tension. We expect to have lower vapor pressure, as we'll talk about later, because of the hydrogen bonding capabilities. Now, if I look at my last molecule here, I have hydrogen directly bonded to oxygen and chlorine bonded to that oxygen. So I have my three lone pairs on chlorine and two lone pairs on the oxygen. Okay, and you might recognize this as hypochlorous acid in water. Okay, so this is capable of hydrogen bonding because hydrogen is directly bonded to oxygen. So in this case, I would say yes. So you're going to find that your ability to draw Lewis structures are going to be very important for predicting the types of intermolecular forces that you have. Now let's see basically a picture that summarizes all the intermolecular forces we've talked about so far in this chapter. We'll consider that all molecules have dispersion forces. That's just from distortion of the electron cloud, causing very temporary dipoles, temporary separation in charge, but in those molecules, so we can always have these weak dispersion forces. They're present in all substances, but some substances have on top of these dispersion forces other stronger interactions. So just remember, dispersion forces are always present. Now if I have a polar molecule, so if I draw my Lewis structure and my molecule's polar, that would predict that you have a permanent dipole for the molecule, so we would have dipole-dipole interactions, which in general is stronger than dispersion forces unless we're considering very high molecular masses, in which case the dispersion forces may contribute enough to actually cause differences in melting points and boiling points and other physical processes. So now if we consider very electronegative differences between very electropositive hydrogens and very electronegative small atoms like fluorine, nitrogen, oxygen, here we get permanent dipoles, but we give them a special name. We say these permanent dipoles are so strong that we call it hydrogen bonding in this case. So those are your three scenarios that we can consider with different types of intermolecular forces and how we can categorize them with respect to molecules as dispersion forces, dipole-dipole forces, or hydrogen bonding. Now I want to stress that if I look at water, H2O, and I ask you what are all of the intermolecular forces present, if I'm asking you to list all of them, well, hydrogen bonding is the strongest interaction, but I need to say, well, it's just a type of dipole-dipole interaction. So dipole-dipoles are also present. We just gave this a unique name because of the strength of the dipole-dipole interaction as hydrogen bonding. And dispersion forces are there as well. So H2O has all three of these type of intermolecular actions occurring simultaneously. And sometimes students don't realize that they still need to consider these other intermolecular forces occurring at the same time. Okay, they're all present. But the hydrogen bonding is the strongest interaction, so sometimes they'll forget and just list the strongest interaction and forget that the others are present as well. Okay, so thank you, everybody. I'd like you to start to try to work on your homework problems and predict the strengths of different types of intermolecular forces, as well as predicting what types of physical property differences there would be between molecules with different strength of intermolecular forces. Okay, thank you very much.